Imagine for a moment you're trying to build like the ultimate digital assistant,
Yeah.
you know,
Okay, I'm imagining. What's it doing?
one that could find the absolute perfect flight route for you. Not just A to B, but considering every single connection, every possible layover, every fluctuating price
Oh, wow.
across the entire globe, all in real time. It's a huge task.
Yeah, that sounds computationally intense, to say the least.
Exactly. Or maybe you're tasked with perfectly scheduling some massive construction project. You've got thousands of interdependent tasks, limited resources, tight deadlines.
Right, the classic nightmare scheduling problem.
Yeah, some problems you just feel it. They're fundamentally, like, impossibly hard to solve quickly. What if there was a way, though, a mathematical framework, to not just feel that difficulty, but to actually prove it,
Ah, to get rigorous about it.
to lay bare the very limits of what computers can efficiently do?
Okay, I see where you're going.
Hey everyone, welcome to Computer Science Tech Papers Summary. I'm Alex, your guide to the big picture and hopefully some of the surprising connections in computer science research.
And I'm Jordan. I'm here to help unpack the precise mechanisms and illuminate the core technical ideas.
And today, we're embarking on a deep dive, a really foundational one.
We are. We're looking at a landmark paper, a true cornerstone that utterly transformed how we understand computational limits.
Yeah, this isn't just any old paper. It's practically the birth certificate for an entire field. We're talking about Stephen A. Cook's 1971 paper, The Complexity of Theorem-Proving Procedures.
Published over 50 years ago, which is kind of amazing.
It is, and it remains profoundly relevant today. It's like finding the original blueprint that, continues to shape modern computing. It's the paper that really gave us the foundational concept of computational hardness, and it laid the groundwork for what we now understand as NP-Completeness.
Even if the term wasn't fully coined or widely used right then, Cook sort of set the stage.
Exactly. This is the document that really for the first time rigorously explained why some problems might just forever remain stubbornly difficult.
You've absolutely hit on its core significance. At its heart, Cook's paper tackles what he called recognition problems.
Recognition problems.
These are really fundamental questions. You're given an input, maybe it's a string of characters, or maybe a complex data structure like a network graph.
Okay.
And you need to determine if that input belongs to a specific set. So, for example, is this long string of digits a prime number?
Right, yes or no.
Or is this complex network, say, like a social network map? Is it structurally identical, isomorphic to a smaller subnetwork within another much larger one?
Got it. Does this pattern exist inside the bigger picture?
Precisely. Cook was intensely focused on the inherent difficulty of these problems. Specifically, how much time and computational resources a theoretical computer, what we call a Turing machine,
The theoretical workhorse.
you need to solve them. How many steps, how much memory, essentially?
And the particular recognition problem he really zoomed in on, the sort of main character in his big proof, was determining tautologyhood.
Right, tautologyhood. It's a bit of a mouthful.
It is. So let's break that down. We're dealing with propositional formulas here.
Okay, think basic logic statements.
Yeah, essentially strings made up of symbols. These often represent simple true-false statements, right? And they're combined with logical connectives like A and D, or R, and not.
Like P and DQ, or not PU or Q. Simple building blocks.
Exactly. Think of simple logical sentences like, it is raining and the sun is shining.
Right, and tautology is a special kind of these formulas. It's one that is always true, no matter what truth values, true or false, you assign to its basic propositions.
Always true, like guaranteed.
Guaranteed. For instance, the statement, it is raining or it is not raining. That's always true, right? It doesn't matter if it's actually raining or not. It's logically inevitable.
Okay, so it's a logical statement that's so fundamentally solid it holds up under every single possible scenario. I get that. But why would recognizing something so undeniably true be considered a hard problem? It seems like it should be easy.
Ah, well, that's the core efficiency question, isn't it? At first glance, recognizing a tautology might seem simple. You could just, list out every possible combination of true and false values for the variables in the formula.
Like a truth table.
Exactly, like building a truth table. And then you check if the formula comes out true every single time.
Seems straightforward enough.
But here's the catch. As these formulas get longer, more complex, with more variables, the number of possible truth assignments just explodes exponentially.
Right.
For a formula with n variables, there are 2n possible assignments. So if you have 10 variables, that's about 1,000. If you have 100 variables, Well, that's more combinations than atoms in the universe,
Okay.
practically.
Yeah, that's not feasible.
Yeah.
Checking every single one becomes astronomically slow.
Exactly. We're talking about computations that could take longer than the age of the universe, even for what seems like a moderately sized formula on paper.
Wow. And this was all happening, you mentioned, back in the early 1970s.
Yep. Early 70s.
A really fascinating moment in time for computer science. It was still kind of finding its feet, but there was this palpable sense of excitement, right? A huge drive to build efficient algorithms for practical problems.
Definitely. Especially in emerging fields like automated theorem proving,
Mm.
early AI. People wanted machines to do things, solve things.
So they needed to know, could we actually build machines that could reliably prove complex logical statements without taking, basically forever?
Precisely. Cook's paper was trying to get at the very root of that question, to define the underlying limits, what's possible efficiently.
Okay, so before Cook came along with this paper, what was the understanding of computational difficulty like? How do people categorize problems?
Well, it was pretty rudimentary, honestly. We had basic notions like solvable or unsolvable. Think of the halting problem Alan Turing proved that's undecidable, unsolvable by any algorithm.
Right, the classic example is something computers just can't do.
Exactly. But beyond that simple solvable, unsolvable binary, there wasn't a really formal, widely accepted way to categorize problems by shades of difficulty.
So, some solvable problems are way harder than others.
Right. We had Turing machines as our theoretical model, and we could talk about how many steps a machine took. But how do you meaningfully compare the difficulty of, say, checking if a number is prime versus solving a really complex puzzle like that subgraph isomorphism problem we mentioned?
Yeah, they feel different.
They do. It was clear some problems were harder than others, but without a formal framework, it was mostly intuition, a feeling, rather than a rigorous mathematical proof.
So Cook basically stepped into this intellectual void and started building that rigorous framework.
That's a good way to put it. He formalized the idea of polynomial time, often denoted as P, or L star, as he called it in the paper.
Let's go. Okay, so
Oh.
polynomial time, P. That's the class of problems we consider efficiently solvable, right?
Correct. These are problems where the time it takes to solve them grows, let's say, reasonably with the size of the input. If your input size doubles, the time might, say, quadruple or grow by a cube, but it doesn't suddenly jump from milliseconds to millennia.
Manageable growth. These are the easy problems, computationally speaking.
Right, relatively easy. But then, crucially, he also brought in this conceptual powerhouse, the nondeterministic Turing machine.
Okay, you mentioned this isn't a real machine.
No, not something you can physically build, and it doesn't involve actual magic or random guessing in the way we usually think of it. It's a theoretical model, a thought experiment.
So what's the experiment?
Imagine a machine that, whenever it faces a choice point in its computation, like should I explore path A or path B, it can essentially guess the right path. Or, another way to think about it, it can explore all possible paths simultaneously.
Like it splits into parallel universes, each trying a different sequence of choices.
Kinda, that's a common analogy. It's in stark contrast to a standard deterministic machine, which has to follow one single fixed sequence of operations, step by predictable step.
Okay.
So while you can't build one, the non-deterministic Turing machine is incredibly powerful for defining complexity classes. It helps us understand the limits of what could be computed quickly if we had this, well, oracle-like ability to always make the perfect choices or explore all options at once.
That's a really powerful image, like having a magical assistant who instantly tries every possible solution to a maze all at once and tells you if any of them lead to the exit.
That's a great way to visualize the power of non-determinism, yeah.
So what does that kind of magical assistant let us understand about problem solving that we couldn't otherwise?
It allows us to define what we now call the complexity class, NP. N for non-deterministic, P for polynomial time.
NP. Okay, I've definitely heard of that.
Right. These are problems where if you had that non-deterministic superpower, you could solve them in polynomial time. Or maybe a more intuitive way to think about NP for deterministic machines.
Yeah.
These are problems where if someone hands you a potential solution, you can verify if it's correct in polynomial time using a regular deterministic machine.
Ah, okay, that makes sense. Like solving a Sudoku puzzle can be really hard, take ages.
Yeah.
But if someone gives you a completed grid,
You can check it really quickly. Check the rows, columns, boxes. That's polynomial time verification, so Sudoku is an NP.
got it. Finding is hard, checking is easy. That's NP.
That's the essence of it. And building on that idea, Cook introduces these things called query machines with oracles.
Oracles. Sounds mystical again.
Yeah, but again, it's purely a thought experiment. An oracle is just a hypothetical black box that can instantly solve one specific problem for free, computationally speaking.
So like a magic button for solving, say, the primality test.
Exactly. You might have an oracle that, given any number, instantly tells you prime or not prime. Or an oracle for any set t, you give it a string, it instantly tells you if the string is in t.
Okay, so it's not about actual magic. It's about asking, what if?
Precisely. It lets us ask this fundamental question. If we could solve problem X instantly using this oracle, what else could we solve efficiently? What other problems could we solve quickly if we had that instant solution as, like, a subroutine?
So it helps understand how problems relate to each other, like dependencies.
Exactly. It helps us understand the hierarchical relationships between problems. It shows which problems are computationally dependent on others.
And that leads us right to the core concept Cook needed to formalize this hierarchy, right?
Yeah.
A precise way to say one problem is no harder than another.
Yes, he introduced P-reducibility. The P stands for polynomial time.
P-reducibility.
Okay. Informally, you can say a set S is P-reducible to a set T if there's a deterministic algorithm, a regular program that can solve problem S, if it has access to an oracle for problem T.
So it uses the T oracle as a helper.
Right. The algorithm takes an input for problem S, possibly transforms it into one or more inputs for problem T, asks the oracle for T for the answers, and then uses those answers to figure out the solution for S and the key constraint.
Let me guess. The algorithm doing the transforming and using the oracle has to run in polynomial time itself.
Exactly. The reduction process itself must be efficient. It can't take exponential time to convert the problem or use the oracle's answers.
Okay, this feels like the crucial conceptual leap.
It really is. What it means, basically, is if you can solve problem T quickly in polynomial time, then you can also solve problem S quickly, because you can just run the reduction algorithm.
So if T is easy, S must also be easy.
Correct. You can systematically convert any instance of S into an instance of T, get the answer from the T oracle, which we assume is fast if T is easy, and convert the answer back, all without a significant blow-up in computational effort.
It's like saying, if you give me a super fast calculator that only does square roots, I can still figure out multiplication problems pretty quickly because I know how to break multiplication down into steps that use square roots, and the breakdown process itself isn't too hard.
That's a great analogy. It shows this clear hierarchy of difficulty. If square roots are easy and I can reduce multiplication to it efficiently, then multiplication is also relatively easy.
And this P-reducibility thing, it has an important property, right? Something about chains.
Yes, absolutely. It's transitive.
Transitive, meaning?
Meaning, if problem A is P-reducible to problem B, AAPB, and problem B is P-reducible to problem C, BAPC, then it automatically follows that problem A is also P-reducible to problem C, AAPC.
Ah, okay. So the no harder than relationship carries through. If A is no harder than B and B is no harder than C, then A is no harder than C. Makes sense.
Exactly. And if you picture this, it means we can create these powerful chains of difficulty. If one problem, say C, is known to be inherently hard, and we can show that other problems, like A and B, reduce to it, then those problems A and B must also be hard.
Why? Because if A or B were easy,
then C would also have to be easy because you could solve it by reducing it to the easy problem. But we already said C is hard, so contradiction.
Gotcha. It's a logical cascade.
Yeah.
It creates this backbone for the whole field of complexity theory. Finding one hard problem can make a whole bunch of others hard, too.
Precisely. And armed with this powerful new tool, P-reducibility, Cook was ready to tackle the big question, which problems are truly the hardest? The benchmarks against which others could be measured.
And his first major target was our old friend, tautologyhood.
Yes. This leads us directly to the centerpiece of the paper, Theorem 1. This provides the central reduction, and the claim is profound.
Okay, what's the claim?
If a set S of strings is accepted by a nondeterministic Turing machine within polynomial time. So in other words, if S is an NP.
Right, the class of problems with easily verifiable solutions.
Then S is P-reducible to DNF tautologies.
Whoa. Okay, wait. So any problem in NP can be reduced to checking if a certain type of logical formula is always true.
Essentially, yes. DNF stands for disjunctive normal form. It's just a specific standard format for these logical formulas. But yeah, the core idea is that this DNF tautology problem is, in a sense, the hardest problem in NP, because every other problem in NP can be efficiently transformed into it.
That's huge. How did he even prove that?
Well, this is where Cook's genius truly shines. The proof is incredibly clever. It involves constructing a specific propositional formula, let's call it AW, based on the computation of any given nondeterministic Turing machine M on a specific input string W.
Okay, so you take the machine M and the input W, and you build a formula AW out of them.
Exactly. And to understand the core ingenuity, you have to think about how he built it. Imagine it like creating a grand logical blueprint of the computation. Cook defined different types of logical variables, propositions, to represent every single detail of the Turing machine's operation at every single step of its potential computation.
Every detail. Like what?
Like pi st could mean tape square s at step t contains symbol psi, or key could mean at step t the machine is in state key, and SST could mean at time t tape square s is the one being scanned by the machine's head.
Okay, so these variables are literally giving us a snapshot of the Turing machine's entire configuration. Its tape contents, its internal state, its head position for every single step of its computation, up to the maximum polynomial time allowed.
Exactly right. It's like a complete historical record of a possible accepting computation, but encoded purely in logic.
Wow. Okay, so you have these variables. Then what?
Then he wove these variables together into this massive logical formula, AW, using ANDs and ORs. But this formula wasn't just random. It was meticulously designed so that each part of the formula asserted a fundamental rule about how a valid Turing machine computation must proceed.
Rules like?
Like, one section would ensure the machine's head only scans one tape square at each time step t. Using ORs to say it scans S1 or S2 or SN, but also using ANDs with knots to say it can't scan psi ANDIJ if I and J are different.
Okay, enforcing the physical limits of the machine head.
Right. Another section would ensure that each tape square S at each time t holds exactly one symbol. Another ensures the machine is in exactly one state at each time t.
Makes sense. Logical constraints reflecting the machine's definition.
Then there are crucial sections that encode the machine's actual transition rules. How it moves its head, what symbol it writes on the tape, and what state it changes to, all based on its current state and the symbol it's currently reading. These clauses link the configuration at time t to the configuration at time t plus 1.
So the formula enforces the step-by-step logic of the machine itself.
Exactly. And finally, the formula also included clauses to set up the machine's initial state, time t0, with the input string W correctly placed on the tape, and crucially, a clause asserting that the machine eventually reaches one of its designated accepting states within the polynomial time bound.
It's remarkable. So if I'm getting this right, he essentially encoded the entire possible behavior of a non-deterministic Turing machine, its every potential move and state change over polynomial time, into a single enormous logical formula.
That's the core idea.
And if that formula holds true, if it's satisfiable, that means the machine could have accepted the input.
Precisely. This is where the magic happens. The abstract operation of this theoretical computer becomes this concrete logical puzzle. The clever part is how ADW is constructed. It is satisfiable, meaning there's some assignment of true-false values to the variables that makes the whole formula true if and only if the nondeterministic Turing machine M actually accepts the input string W.
So a solution to the formula corresponds to a valid accepting computation path of the machine.
Exactly. If the machine accepts W, then there exists a sequence of configurations demonstrating this acceptance, and that sequence directly translates into a satisfying assignment for AW.
Okay, and if the machine doesn't accept W?
Then no such accepting computation exists, and therefore there's no way to assign truth values to make AW true. So AW is not satisfiable.
And if AW is not satisfiable?
Then its negation, AW, not AW, is a tautology. Because if AW is false under all assignments, then AW must be true under all assignments.
Ah, there's the link back to tautologies.
There it is. So the problem of determining if the nondeterministic machine M accepts the string where, which is the general form of any problem in NP, is reduced to determining if the formula AW is a tautology.
Wow.
And the paper also notes that this AW can be easily converted into that specific format, disjunctive normal form, or DNF, without much extra work. So the reduction is specifically to DNF tautologies.
So let me recap. We want to know if our magical non-deterministic machine accepts a string W. Cook shows we can build this giant logical puzzle, AW, where the puzzle has a solution only if the machine accepts the string.
Right.
And the negation of that puzzle, AAW, is a tautology. Always true. If and only if the machine doesn't accept W.
You've got it. It's like a perfect logical mirror.
It's like a logical trap. And the truly amazing part is that this whole incredibly complex construction of AW, building this massive formula, can be done efficiently, in time, bounded by a polynomial in the length of the input W.
Yes. That's absolutely critical. The size of the formula AW and the time needed to construct it are polynomial in the size of the input W and the polynomial time bound of the machine M. This ensures that the reduction itself doesn't make the problem harder. The transformation is efficient.
Okay? That seals the deal for P-reducibility. Wow.
So with that incredibly clever construction established, Cook's paper then unveils some truly groundbreaking results. It starts drawing lines in the sand for computational difficulty.
Okay, what comes next?
Well, a direct corollary to Theorem 1 is huge, since any problem in NP can be reduced to DNF tautologies in this way. It means that because many common practical problems, or sometimes they're complements, like asking if something is not a member of a set, are known or suspected to be in NP.
Like scheduling, routing, packing problems.
Exactly. All those problems that seem hard but where you can check a solution easily, they are all, by extension, P-reducible to DNF tautologies.
So if you found a magical, fast way to solve DNF tautologies,
you'd instantly have a fast way to solve all those other problems in NP too. It confirms that DNF tautology is, in a sense, a universal representative for the difficulty of NP problems.
Okay, that's a massive implication already. But Cook didn't stop there, right? He used this P-reducibility tool to show connections between seemingly different problems.
Exactly. He pulled back the curtain on an entire family of problems, proving they were all fundamentally intertwined in their difficulty. This leads us straight to Theorem 2.
Theorem 2. What does it say?
It's a profound revelation for computational complexity. It states that the following specific sets, or problems, are all P-reducible to each other in pairs.
Meaning?
Meaning they all share the same polynomial degree of difficulty. They are fundamentally equally hard from a computational perspective. If you solve one efficiently, you solve them all efficiently.
Okay, lay them on me. What's in this equally hard family?
All right, first on the list is our original problem. Tautologies, just general propositional formulas that are always true.
Got it. The starting point.
Second, DNF tautologies. Tautologies written in that specific disjunctive normal form we just discussed. The paper rigorously shows these two are interreducible.
Okay, makes sense given Theorem 1.
Third, and this is fascinating, is D3. This is a specific restricted subset of DNF tautologies. In D3, each disjunct, which is an OR clause in the DNF formula, is made up of, at most, 3 literals, where a literal is just a variable like x, or its negation like not x. Wait, actually, let me rephrase that slightly. Based on the outline, D3 is where each OR clause, disjunct, has at most 3 A and D clauses, conjuncts, and each of those conjuncts is simple. The exact definition is technical, but the key number is 3.
Okay, so D3 is a limited version of DNF tautologies. Why is that significant?
It's incredibly significant. Cook showed that you can take any DNF tautology, no matter how big and complex, and efficiently transform it in polynomial time into an equivalent D3 tautology.
You can simplify any DNF tautology down to this restricted D3 form.
Yes, while preserving whether it's a tautology or not. This means that even this highly restricted version of the problem, D3, is still just as hard as the general DNF tautology problem, and thus just as hard as any problem in NP.
Wow, so the difficulty isn't just in the overall size, it's something fundamental captured even by this limited structure with the number 3.
Precisely. It really isolates the core difficulty. It's not about having hugely complex clauses. Clauses with just 3 parts are enough to capture that hardness.
Okay, that's amazing. What's the 4th problem on the list? You said this is where it gets practical.
Yes. The 4th problem shown to be equivalent in difficulty is subgraph pairs.
Subgraph pairs.
This is the problem where you're given 2 finite, undirected graphs-think networks of nodes and edges. Let's call them G1 and G2. The question is, does G1 exist as a structurally identical copy within G2? Is G1 isomorphic to a subgraph of G2?
Okay, this is where it gets really interesting for practical computer science. We've jumped from abstract logic formulas like tautologies and D3 to a very concrete, visual, real-world kind of problem involving graphs. Graph problems are absolutely everywhere.
They really are. Social networks, designing integrated circuits, figuring out protein interactions in biology, mapping the internet, optimizing delivery routes.
So knowing that this subgraph problem is fundamentally as hard as recognizing a logical tautology, that's a huge insight for anyone working in those areas, right?
Absolutely. Imagine trying to find if a specific complex molecular structure, G1, is embedded within a much larger, more convoluted known protein, G2. Cook's work tells us that problem likely shares the same underlying, potentially exponential difficulty as those abstract logical puzzles.
How did he even connect D3 to graphs? That seems like a big leap.
The proof for this reduction, reducing D3 to subgraph pairs, is also quite intricate and clever. He shows that for any given D3 formula, you can construct two specific graphs, let's call them G1 and G2, based on the structure of the formula.
Okay.
And the construction is done in such a way that the D3 formula is not a tautology if and only if the graph G1 can be embedded as a subgraph within the graph G2.
So a falsifying assignment for the D3 formula corresponds directly to finding this specific subgraph.
Essentially, yes. A satisfying assignment for the negation of the D3 formula, meaning the original D3 formula is not a tautology, corresponds to the existence of a specific kind of mapping, a subgraph homomorphism, from G1 to G2. And again, critically, this construction of the graphs from the formula can be carried out in polynomial time.
Maintaining the P reduction. Wow. So this is the real punchline then for many people in the field, right?
It really is.
If you could find a polynomial time solution for any one of these problems, whether it's abstract tautologies, the restricted D3, or the very tangible subgraph problem,
You'd effectively have a polynomial time solution for all of them, and by extension, for all problems in NP.
it means these seemingly distinct problems, one from logic, one from graph theory, are, at their computational core, the same beast, just different masks for the same underlying difficulty.
That's a perfect way to summarize theorem 2. It established this foundational equivalence class of hard problems.
Now, you said what's not on the list is also interesting. What problems did Cook consider but leave out?
Right. Cook was very deliberate, and his comments on excluded problems are quite insightful, especially with hindsight. For instance, he mentions the problem of determining if a number is prime.
Yeah, primality testing seems fundamental.
It is.
Yeah.
But Cook notes that reducing tautologies to primes would likely require deep results in number theory. He sensed it was different.
And was he right?
He was. Much later, in 2002, Agrawal, Kayal, and Saxena famously showed that primality testing is actually NP. It can be solved efficiently in polynomial time.
Wow. So it's not as hard as tautologies or subgraph isomorphism.
Correct. Cook's intuition back in '71, sensing that barrier between logic combinatorics and number theory, was spot on. His caution highlighted the complexity of bridging these different mathematical domains.
Okay. What else was left out?
Another really interesting one is isomorphic graph pairs. This isn't subgraph isomorphism, but testing if two graphs, G1 and G2, are exactly identical, perfectly isomorphic to each other.
So not finding G1 inside G2, but asking if G1 is G2, just drawn differently.
Exactly. Cook mentions a conjecture by a researcher named Corneal. He notes that if tautologies could be reduced to this graph isomorphism problem, it would probably upset Corneal's belief that graph isomorphism could be solved in polynomial time.
And where does graph isomorphism stand today? Is it P? Is it NP-complete like tautologies?
That's the fascinating part. It's still unresolved. Graph isomorphism, GI, is one of the very few natural problems that's in NP, but is not known to be solvable in P and is also not known to be NP-complete.
It's a Dumbo.
Kind of. It's
Huh.
widely believed not to be NP-complete, meaning it's likely easier than tautologies and subgraph isomorphism, but no polynomial time algorithm has been found yet. It sits in this mysterious intermediate complexity class. Cook's comments, again, showed remarkable foresight about the subtleties here.
Okay, one more really important exclusion. You mentioned D3 was on the list. What about D2?
Ah, yes. D2. This is the set of DNF tautologies where each OA clause has at most two literals or conjuncts, depending on the exact formulation, but the key is the number 2.
So just like D3, but with 2 instead of 3.
Right. And Cook explicitly states that D2 is in L. His notation for PD2 can be solved in polynomial time.
Whoa, so going from 3 terms per clause down to 2 makes it easy.
Relatively easy, yes. Polynomial time solvable. Therefore, Cook says D2 cannot be added to the list of equivalent hard problems in Theorem 2 unless...
Unless P equals NP, unless all those hard problems were actually easy all along.
Exactly. Unless all sets in the list are in L, as he puts it, This provides a crucial contrast. It shows this incredibly sharp boundary. A seemingly tiny change in the problem definition from 3 turns to 2 dramatically drops the computational complexity.
That's amazing. It's like finding a sheer cliff face in the landscape of computational difficulty right there between 2 and 3. It's not just a gradual slope, it's a fundamental shift.
It really highlights how sensitive complexity can be to the exact structure of the problem. It's not just about overall size, but these critical structural parameters.
So Cook mainly focused on these yes-no problems, the propositional calculus. Did he touch upon more complex logic?
He did. In section 3 of the paper, he briefly delves into the complexity of the predicate calculus. This is a more expressive logical system. It allows for variables, functions, relations, and quantifiers like for all x, or there exists an x.
Okay, the kind of logic you use for more serious mathematical statements.
Right. But predicate calculus comes with a big challenge. Determining satisfiability or validity is generally undecidable.
Undecidable. Like the halting problem again?
Exactly like the halting problem. There's no algorithm that can take any arbitrary predicate calculus formula and guarantee to tell you if it's satisfiable or valid, and also guarantee to halt on all inputs.
So if you can't even guarantee an answer, how do you measure the efficiency of a theorem-proving procedure for it? It seems like the concept breaks down.
It does in the standard sense. You can't just measure time as a function of input size n because the procedure might never halt. So Cook proposes a different measure, specifically for evaluating the efficiency of proof procedures for unsatisfiable formulas, the dual of tautologies. He calls it TQK.
What did that stand for?
Well, the T is time. Q refers to the specific proof procedure being measured. The K is more subtle. It relates to Herbrand's theorem from logic.
Herbrand. Okay. Briefly.
Very briefly, Herbrand's theorem says that if a formula in a certain form of predicate calculus is unsatisfiable, logically contradictory, you can always demonstrate this by looking at a finite set of its substitution instances, basically. Simpler, ground-level examples derived from the formula. Cook defines EA as the size K of the smallest such set of instances needed to show the formula A is inconsistent.
So K is like a measure of how deep you have to go, how many simple examples you need to check to find the contradiction in an unsatisfiable formula.
Exactly. It's a measure of the proof's complexity in a logical sense. If A is actually satisfiable, then A is undefined or infinite.
Okay, so K measures the proof complexity. How does TQK use this?
TQK is defined as the time the proof procedure Q takes to halt and find the inconsistency, given that the proof complexity A is no more than K, and also assuming the formula A itself isn't too long, specifically its length A is at most log 2K.
So it's measuring. How fast can procedure Q find a proof of inconsistency if we know what proof of complexity K exists and the formula isn't too big compared to K?
Precisely. It's a way to measure efficiency relative to the inherent logical complexity K of finding the contradiction for formulas that are contradictory.
Okay, that's a clever way to handle undecidability. What did Cook find out about this TQK?
He presented Theorem 3, which gives bounds on how fast any such procedure Q can possibly be. Part A provides a lower bound. Any procedure Q must take time TQK that grows at least as fast as score code K2. There's a fundamental minimum effort required.
So you can't possibly find these proofs instantly. Even if K is small, there's built-in difficulty.
Right. And part B provides an upper bound. He shows there exists a procedure Q whose time TQK is roughly proportional to K2K log K2.
Whoa, okay. That upper bound has a 2K in it. That looks exponential in K.
It is. And notice the huge gap between the lower bound, roughly square root of K, and the upper bound, roughly K times 2 to the K.
Yeah, that's a massive difference. What does that gap mean?
It means that in 1971, we knew there was some procedure that worked within that exponential upper bound, but we didn't know if it was possible to do dramatically better. Maybe something closer to the square root lower bound, perhaps even polynomial in K. Cook himself points out this gap later.
Okay, so a big unknown there. And did he connect this TQK back to the P versus NP stuff?
He did in Theorem 4. This theorem makes a very strong connection. It states that if this measure TQK were bounded by a polynomial in K, so if you could find proofs of inconsistency really efficiently relative to their logical complexity K, then a deterministic Turing machine could simulate a non-deterministic machine running an exponential time 2n using only polynomial time relative to that 2n, that is, in P2n, time for some polynomial P.
Okay, that sounds technically dense, but seems important. What's the intuition?
The intuition is that finding these predicate logic proofs efficiently, polynomial TQK, would imply a surprisingly powerful speed-up for deterministic machines trying to simulate non-deterministic ones, at least in the realm of exponential time computations. It links the efficiency of these logical proof systems directly back to fundamental questions about the power of non-determinism versus determinism.
So if you solve this logic proof problem efficiently, you'd basically collapse the difference between deterministic and non-deterministic machines for exponential time.
Something along those lines, yes. It would be a huge theoretical breakthrough, suggesting deterministic machines are much more powerful simulators than previously thought.
It's amazing how Cook keeps connecting these different threads. Propositional logic, predicate logic, Turing machines, P, NP. It's all interwoven.
It really is. And what's also striking is how open he is about the limitations and the open questions remaining from his own work. That's often a sign of truly foundational research.
What specific gaps did he point out?
Well, for one, despite providing all this compelling evidence that tautologies is difficult, showing all of NP reduces to it, he explicitly states he provides no such lower bound here for the actual time required to recognize tautologies on a deterministic machine. He didn't prove it couldn't be done in polynomial time.
Ah, so he established its central importance and hardness relative to other problems, but didn't prove it was absolutely hard in terms of P versus NP.
Exactly. That crucial piece, proving tautologies is not NP, was left as the major open question.
And you mentioned the TQK gap earlier.
Yes, that large gap between the lower and upper bounds for TQK in Theorem 3. He points this out and explains the implications we just discussed. He notes that a polynomial TQK would imply that P2n deterministic simulation of 2n non-deterministic time, which he says is contrary to experience.
Contrary to experience, what kind of experience was he referring to back then? Was it just a gut feeling from the early days of algorithm design?
Pretty much. In those early days of computer science, people were already running headfirst into these immense combinatorial explosions when trying to solve certain practical problems. Algorithms for things like scheduling or network optimization or even early game AI, they just rapidly became intractable as the problem size grew.
So the practical reality felt exponential.
Right. So while a formal proof separating these complexity classes was missing, the practical experience of actually trying to implement solutions already strongly suggested that you couldn't just magically simulate exponential non-deterministic power with only a polynomial overhead on a deterministic machine. His intuition was deeply rooted in the observed computational reality of the time.
And he also had caveats about TQK itself.
Yes, he humbly admits that his proposed measure TQK is probably too crude. He suggests that better, more refined measures might need to be functions of several variables, not just this single k. This self-awareness, this openness to future refinement is really admirable.
Absolutely. It really underscores why this paper is so exciting, isn't it? It doesn't just slam dunk answers, it brilliantly sets up the next generations of questions. It's like opening a door to a whole new landscape of research.
It truly is an invitation to further research, defining an intellectual frontier.
And this brings us, inevitably, to the huge, unspoken, well, almost spoken conjecture implicitly laid out in this paper, the P versus NP problem.
It's hovering over everything, isn't it? Cook strongly suggests that tautologies is a good candidate for an interesting set not in L, his term for P.
A good candidate for being hard.
Yes. And he explicitly states that proving tautologies is not in L would be a major breakthrough in complexity theory.
This is it. This is the moment. The genesis of P versus NP as we know it. One of the 7 Millennium Prize problems from the Clay Mathematics Institute. $1 million on the line.
And Cook's paper is where that monumental question truly crystallizes. It directly hints, based on his results, at the possibility that P problems solvable deterministically in polynomial time is fundamentally inherently less powerful than NP problems verifiable in polynomial time, or solvable non-deterministically in polynomial time.
And tautologyhood, or its complement satisfiability, SAT, becomes the cornerstone of this question, sort of master problem for NP. If you can show it's hard, then P cannot equal NP.
Precisely. He also draws that powerful analogy to the halting problem.
Right, remind me.
He notes that if L plus, his term for NP, is the analog of recursively enumerable sets in computability theory, then determining tautologyhood, which is an NP, or rather its complement SAT is the analog of the halting problem, which is recursively enumerable, but not recursive decidable.
So NP is like the listable problems, and tautology's L is like the hardest listable problem, analogous to the halting problem being the hardest listable problem in the older theory.
That's the spirit of the analogy. But then he points out a crucial difference. The standard proof technique used to show the halting problem is undecidable, the diagonal argument.
The self-referential trick.
Apparently cannot be adapted to show tautologies is not in L, as Cook writes.
So the analogy holds in spirit, but the proof doesn't carry over. It's like we found a spiritual sibling to the unsolvable halting problem. But the weapon that killed the first dragon doesn't work on this one. The mystery deepens.
Exactly. We have this problem that feels as fundamental and hard sitting at the top of its class, NP, but proving its hardness requires entirely new techniques which still haven't been found over 50 years later. The path to resolution is much, much more subtle.
Did he mention any existing algorithms for these problems?
Briefly, he touches upon the Davis-Putnam procedure, which was an existing method back then for tackling satisfiability, SAT, the duel of tautologyhood, finding if a formula can be true.
What did he say about it?
He notes, interestingly, that he couldn't find specific examples of formulas that would force the Davis-Putnam procedure to require more than polynomial time, nor could he establish a tight upper bound for its performance in general.
So even for practical algorithms that seemed reasonably efficient on many inputs, the theoretical worst-case behavior was still mysterious.
Yes. It highlights the practical challenges. Even for procedures that often work well, proving concrete lower bounds or tight upper bounds on their performance is notoriously difficult. Theory and practice can diverge quite a bit.
Okay, so summing up the impact here, what Cook's paper fundamentally did was provide the bedrock concept for NP-completeness.
Absolutely. Even if the term NP-complete and its widespread recognition came slightly later, particularly with Richard Karp's incredible follow-up paper in 1972, which showed many more common combinatorial problems were also equivalent in difficulty.
Like the traveling salesperson problem, set cover, etc.
Right. Karp built directly on Cook's work, using P-reducibility to massively expand the list. But the blueprint, the core idea of finding a hardest problem in NP via reduction, was undeniably laid out by Cook.
Cook showed us how to identify such a problem. That idea of finding complete problems for a complexity class.
Yeah.
That's the powerful tool, right? It gives us a benchmark.
Exactly. It's incredibly powerful. If you can prove your new tricky problem is NP-complete by reducing, say, SAT or subgraph isomorphism to it, you immediately know it's at least as hard as this whole known family of notoriously difficult problems.
It's like saying, congratulations, you've discovered another Everest of computational difficulty. Don't waste your time looking for an easy way up.
Precisely. And as we've discussed, the major breakthrough Cook anticipated proving tautologies is not NP, which is equivalent to proving P&P. That remains one of the biggest open questions in all of science. The Millennium Prize problem.
Let's just linger on that P vs NP impact for a second. If somehow P did equal NP, what would happen?
Oh boy. Well, first, modern cryptography would just collapse. Anything based on the presumed difficulty of factoring large numbers or discrete logarithms or lattice problems, gone. Secure online banking, communication, everything would be broken overnight.
Okay, chaos. What else?
On the potentially positive side, optimization problems that currently plague us would become efficiently solvable. Perfect logistics, finding the absolute best drug molecules for diseases by searching vast chemical spaces, designing optimal circuits, potentially even breakthroughs in AI reasoning and planning.
So truly optimal solutions for incredibly complex systems would just be calculable.
If PNP and the polynomial time algorithm was actually practical, yes, it would be a world-shattering transformation, accelerating scientific discovery and engineering optimization at an unimaginable pace. Imagine AI that could truly find the optimal strategy for almost anything.
A double-edged sword, then. Unprecedented power, unprecedented vulnerability.
Absolutely. Now flip that. If PNP, which is what almost everyone suspects,
Yeah, the safe.
then it means there are fundamental, unavoidable limits. We live in a world where certain perfect solutions are simply out of reach for efficient computation, possibly forever, no matter how clever our algorithms or how fast our computers get within polynomial bounds.
And Cook's paper is really ground zero for understanding why that might be the case. It frames that entire landscape.
It does, and this understanding has had a massive transformative impact on practical algorithm design over the last 50 years.
How so?
Because knowing a problem is, NP Hard tells developers and researchers, don't waste your time searching for a guaranteed, always fast, always optimal algorithm, because it's almost certainly impossible.
So it redirects effort.
Exactly. It shifts the focus. Instead of chasing the impossible perfect solution, you work on approximation algorithms, algorithms that guarantee a solution within, say, 10% of the optimum. Or you develop heuristics, clever rules of thumb that work well most of the time on typical inputs, even if they fail occasionally or aren't provably optimal. Or you design algorithms for specific, restricted cases of the problem that are tractable.
So it's not about giving up, it's about being smarter, more strategic about what kind of solution is achievable.
Precisely. It's about understanding the inherent limitations and designing around them intelligently rather than banging your head against a wall of exponential complexity.
And Cook's call for better complexity measures, especially for things like theorem provers, is still relevant.
Very much so. The field continues to refine how we evaluate the efficiency of algorithms, especially for problems where the output isn't just yes-no, or where we care about average case performance or performance on specific types of inputs. Cook's paper isn't just history, it's a living document. Its questions continue to inspire research into the fundamental limits and capabilities of computation, influencing everything from quantum computing to machine learning theory.
Okay, so let's hit the speculative corner then. We talked about PMP. Let's stick with the PMP world, the one we probably live in. What does accepting those limits mean for tackling the really grand challenges, like, say, accurate long-term climate modeling, or truly personalized medicine based on genomics, or building truly human-like general AI?
That's a great question. If PNP, it implies that for these incredibly complex systems, we might never achieve perfect, guaranteed, efficient prediction or optimization in the absolute sense. Our climate models will always have inherent uncertainties arising from computational limits, not just measurement limits. Personalized medicine might rely on powerful statistical correlations and approximations rather than perfectly modeling every single biochemical interaction from first principles efficiently.
And for AI?
For AI, it might mean that true general intelligence, if it relies on solving NP hard problems optimally all the time, might be fundamentally harder to achieve than we think. Or, perhaps more likely, it means that biological intelligence, and maybe successful AI, relies more on good enough solutions, heuristics, pattern matching, and approximations, rather than brute force optimal calculation for every hard problem it encounters. Maybe the secret isn't breaking P versus NP, but finding clever ways to work within its constraints.
So embracing cleverness, approximation, and finding strategic shortcuts becomes the name of the game, rather than just raw computational power.
I think that's a likely implication, yes. We have to strategically pick our battles, focus computation where it yields the most insight, and accept that some perfect answers might remain perpetually beyond our efficient reach. Cook's work essentially sets the boundaries of that playing field.
Okay, let's try and wrap this up. A TLDR for this incredible deep dive.
All right. Stephen Cook's 1971 paper, The Complexity of Theorem-Proving Procedures. Fundamentally, it introduced the concept of P-reducibility, a formal way to say one problem is no harder than another efficiently.
Right, the key tool.
Using this, he showed that the problem of determining if a logical formula is a tautology, always true, is incredibly central. Specifically, any problem in the class NP can be efficiently reduced to it.
Making it a hardest problem in NP.
Exactly. And then, crucially, he showed that several other problems, including the restricted D3 tautology problem and the very practical subgraph isomorphism problem, are all P-reducible to each other and to tautologies. They form an equivalence class of equally hard problems.
The first identified family of NP-complete problems.
Correct. And in doing all this, he laid the rigorous conceptual groundwork for the P versus NP question: is finding solutions inherently harder than verifying them? A question that remains one of the deepest mysteries in science and continues to shape our entire understanding of computation and its limits, even half a century later.
Wow, okay. So, the next time you're faced with a problem, maybe at work, maybe just a puzzle that just feels impossibly complex, impossibly tangled, remember Stephen Cook's 1971 deep dive? It's such a profound reminder that sometimes the most revolutionary insights come not from finding the solution itself, but from rigorously understanding why a solution might be so incredibly hard to find in the first place. It just makes you wonder, doesn't it? What other impossible problems out there might be secretly connected by an invisible thread of computational difficulty, a thread we're only just beginning to perceive?
What other fundamental boundaries of computation were still waiting to be discovered? It's an ongoing quest.
Absolutely. Well, thank you for joining us on this deep dive into the very heart of computational complexity. We really hope this exploration inspires you to continue your own deep dives into the truly fascinating world of computer science.